Okay, let's begin my today's session. Many students have already joined. Today I'm going to continue about my discussion on simplex method because the discussion is not yet complete. And to do this, first of all, I have decided to select the problem which actually I gave you in the CA1 examination. That problem I'm going to select, and I'll try to show it by the simplex method, how to know whether it has unbounded solution or no feasible solution, because feasible region is falling in some quadrant, which are not actually a feasible quadrant for LPP solutions. So that problem I'm going to select, and I'm going to do it by the simplex method to show how this particular thing occurs. Okay. Now, let me write the question first of all. The question was, just a minute. Max of z x plus y subject to x minus y greater than or equal to 0, two x minus y less than or equal to minus 2, 2x minus y less than or equal to minus 2, and x comma y greater than or equal to 0. This particular problem, actually, if you draw the graph, this particular problem has no feasible solution because the feasible region falls in the second quadrant. Okay, so if you draw the graph, the answer will come out as it has no solution, as the feasible region falls in the second quadrant. Sorry, not second quadrant, third quadrant. Falls in the third quadrant. Okay. Now, in my last class, we did the problem using simplex method, but we found some unique solution for the problem. Now, this time I'm going to show how the changes occur in the simplex method, and how do we get to know that for a given problem, the solution, the simplex table actually indicates that the system has no solution, because something is going to happen with this in the simplex method, in the simplex table, so that you can identify that, yeah, this particular system has no solution. This is point number one. Point number two is, in the last problem, the problem that we did, the question was having only lesser than type inequality. Here, one lesser than type inequality is there, but with that also we have another inequality which is of greater than type of inequality. We know for lesser than type inequality, we need to add something to the left hand side of the inequality to balance the system. Okay, but if we have the greater than type of inequality, then what we need to do has not yet been discussed. So these are the two important points that we are going to cover in our today's lecture. The method that I'm going to describe is simplex method, but it has a special name. This name is called BGAM method. BGAM method. BGAM method, or sometimes it is also called artificial variable technique. Artificial variable technique. Okay. Now, this particular method is some sort of generalization to the simplex technique, and therefore we are going to, most of the part of this particular technique will remain same, but there will be a few differences, such as greater than type inequality is present, so we have to deal with that. And since, as you can see, that a name big M is there, so there must be something extra to this particular problem. This M represents something, okay, for which the name has been given, such a name has been given to the method. So that parts, those parts will be covered in today's lecture. So first of all, let's begin and let's try to figure out how to make this particular system into a system of equation. First of all, to start with, as you know, step number 1, we shall do nothing with the objective function. The objective function, first of all, will remain not same. It will contain some extra variables, but first of all, let me write it as max z is equal to x plus y. Something extra will come besides it. First of all, let us change to the constraints. Subject to, how many constraints are there? There are 2 constraints. So you see, there is some kind of, conventions which are actually followed in simplex method and simplex algorithm, as well as in linear programming problem. The conventions, one such convention is the following. We do not keep anything negative on the right hand side of the inequality. I'm writing the convention over here. These conventions are not specifically mentioned in any book, but I'm telling you that you have to note it down somewhere. One of many conventions that I discussed in the previous lecture also, that how to select the variables that will be termed non-basic and how to find the basic variables. Another convention is that, and I'm marking this in red color, never to keep anything negative on the right hand side of inequalities. Okay, so you see here in the inequality there is a negative number on the right hand side. First of all, before we begin anything on the with the simplex method, we'll try to make it positive. So this is very simple. What we need to do is that the first inequality will not change. First inequality is on the right hand side, we have greater than or equal to 0. The second inequality, we will multiply both the sides by -1 and we will get minus 2x plus y greater than or equal to 2. X comma y greater than or equal to 0. So we are multiplying both the sides by -1. Okay. So this is my new system. This is my step number 1. We don't want to keep anything on negative on the right hand side of the inequality. This is the first part. And now, once we do this, what happens to the system is that the system is no longer containing any inequality which is of lesser than type. So obviously, the knowledge of our previous lecture in which we discussed about slack variable will not be working out over here. So all the inequalities have now become greater than type of inequality. So we have to introduce a new set of variables which will be called as surplus variable. Okay, this is the first part. Another important part, and I will forget if I don't mention it right now. Remember this point, note it down somewhere in your copy. The simplex method algorithm suitably devised to deal with maximization type of problem. Remember this vital point always. Maximization type of problem. Today, in today's class, if I forget, I will try to discuss something about this particular point. But once I finish the current problem, if I forget, please do remind me that this particular point needs to be discussed. Okay, at least 1 or 2 lines I need to tell something tell about this particular statement. If I forget, please remind me. Someone please remind me once I finish the problem. So this is another type of checking that before we start doing the simplex method, that I actually haven't told you. I didn't tell you in my last class that before I start the simplex method, I need to check whether the problem is a maximization type or not. If the problem is not of maximization type, it is a minimization type of problem, then we have to do something with that. First of all, we have to convert the system into maximization type, and then only we can apply the simplex method. But how to convert that, I will be discussing later on. Now let's go to the next part, step number 2. And in step number 2, I'm going to make the inequalities as equalities. Okay. So first of all, let's deal with the inequalities. Subject to now in the in the previous class, when we had a lesser than type inequality, we introduced slack variable. Now on the left hand side portion, now in this inequalities, left hand side portion is larger than the right hand side portion. So previously we added something to the left hand side. Now we are going to subtract something from the left hand side to balance the system, which is quite obvious. So we'll write x minus y minus s1 greater than equal to 0. Okay. Keep some part blank over here. This blank that I have kept over here is intentionally kept. Okay, so I'm not telling you right now why these blanks are kept, but it is intentionally kept. So you also keep some portion blank in your copy. This is the first part, and this is easily understandable that we want to balance the system, and therefore from the left hand side of the system we are going to subtract something. Okay, and it becomes inequality. The variable that is subtracted is actually called the surplus variable. The variable that is subtracted from LHS of the system to balance the system is called surplus variable. The previous one is called slack variable, and this is called surplus variable. So we have got one surplus variable, which is S1. Now the second one, we write minus 2x plus y, and another surplus variable will be added, that is minus S2, which will be equal to 0. And we will take, you see that it will be better if I write the equality, this particular portion a bit further from the system. I'm writing over here. Now you see this sort of thing that I have written S1 and S2 sort of diagonal, which implies, as in previous case, that S2 is present, S2 is not present over here, and S1 is not present over here. So we are going to keep it some sort of diagonal over here. Okay. Now you see that there will be some sort of change in the objective function. So I'm going to reintroduce the objective function with a new name. The objective function is introduced with the name z prime. As you all know, z prime is physically it is different. I mean, by shape it is different from z, but it is well connected to z. I mean, whatever you do with z prime, z will be affected by just like that. But their structures are different. In Z, only original variables are present. In Z prime, some new variables are also present. So they are structurally different. Okay. Now, we are going to introduce the surplus variable in the new objective function. So x plus y will remain same. Surplus variable are also one type of physical variable. Surplus variables are also one type of physical variables which do not have any practical significance, just like our slack variable. Slack variables per unit contribution to the objective function is 0. It is considered to be 0, so that our objective function's characteristics doesn't change. But surplus variable will also be considered as 0. Its per unit contribution will be considered as 0. So for each of the surplus variable that we have introduced over here, we will apply the per unit contribution to be 0. So we will write plus 0 S1 plus 0 S2. Okay. So this is my new objective function. And below that, we will write xy S1 S2 greater than or equal to 0. Okay, no problem. Up to this is no, we do not have any problem. Oh, one thing that I actually wrote incorrectly, you have also not noticed. The right hand side was 2 actually, so this should be 2. It is not 0. Minus 2x plus y minus s2 is equal to 2. Now you may ask me at this point, why did you keep this parts blank? I mean, this part is blank is quite understandable because S1 is absent. Because if you write explicitly, you can write it as plus 0 into S1. So 0 S1 is actually absent over here, and you can write plus 0 into S2. But we don't have to do so. It is quite understandable. But besides S1 and S2, something is actually, I mean, these blank portions are actually there, which bear some sort of meaning, which I have not yet told you. But I'll tell you very shortly. But before that, I want to show you why, what is happening if I change the system this to that. What will happen? Okay. So I'm deleting this definitions that I have written over here, this convention part and this definition of surplus variable. I'm deleting this part. And as you know that at this point, step number 3 says that you are going to count the number of variables and number of equations from here. So number of equations at this stage is equal to 2, and number of variables at this stage is equal to how many variables are present over there? 1, 2, 3, 4. 4 variables. So the number of non-basic variables whose values will be assumed 0 is 4 minus 2, that is 2. So what it is saying, just like our previous previous discussion, it is saying that number of non-basic variable is actually 2, because it is the difference of the number of variables and number of equations. And among these 4 variables, we need to choose 2 variables whose values will be given 0. Okay, all right, no problem. Up to this, we all know. So, and we all know that the convention is to start with the original variables. Okay, in the previous lecture also I told you that the convention is to start with the original variables. So we don't consider the slack variables to be 0. We first start with the original x and y, and once they are exhausted, we do something. So here also we'll keep the same convention, and we'll consider the non-basic variables as non-basic variable. This will be chosen as x and y. These are my non-basic variables. and their values will be given 0 and 0. Okay. Now you see one thing, one particular part. Once I put these values of the non-basic variables in the equation, what do we get? What are the values of the basic variable? Can anybody tell me? If I put x equal to 0 and y equal to 0 in the equation, in these equations, what basic variables will we get and what are their values? Anybody please tell me.
Sir, I think we
No,
can get the. Sir, I think we can.
I think. Don't say I think. Say I will get.
Oh, sir, I will get the value of S1 and S2.
What are the what will be those values?
Sir, 0 and 2. Minus
So
S1 equal to 0, minus S2 equal to 2.
So what?
Minus.
So what?
S1 equal to 0.
Minus S1 equal to 0 means S1 is how much?
S1 is 0.
Okay, and what will be the value of S2?
2, sir, 2.
Minus 2.
Sir.
Minus 2, sir.
Yes, minus 2. So you will write here S1 equal to 0 and S2 equal to minus 2. Okay, no problem. But now you carefully observe. In LPP, always we deal with the physical variable. And I always told you, I told you that these physical variables cannot be negative variables. They cannot have negative values. These physical variables are always non-negative. This is present in the model of LPP itself. By this term, this is called the non-negativity restriction. This is not only talking about the original variables, but any variable that you are going to introduce in the system, any variable, whether be it slack or be it surplus, you are going to introduce into the system, they need to be physical, and whether they have a physical significance or not doesn't matter, but their feature will be the characteristic feature cannot be negative. Never they can have any negative value, even if during the process of simplex method these variables retain some values, they cannot be negative. It is always need to be positive, always non-negative. Either it can be 0, it can be positive. We do not have any problem with S1. Super fine, S1 equal to 0. But we do have some problem with S2 because it is violating the rule of non-negativity constraints. S2 is coming as minus 2. Now here is the catch. That's why I have kept these parts blank, because whenever a surplus variable is introduced, along with that as a partner, another variable is introduced, which are called artificial variables. So one surplus variable associated with plus A1, one artificial variable, another surplus variable associated with plus A2, another artificial variable. And actually, my number of variables are not xy, this number of variables are not 4. Actually, my number of variables are more than that. Actually, it is 6. So how many variables do we have right now? 6 variables. What are they? X, Y, S1, S2, A1, A2, and these are greater than or equal to 0. So you can make, some students may have asked me who are actually noting down this example in their copy, fair copy. They may ask me that, sir, you are actually doing it's not good. You could have told us, we could have kept some space. We have written so many things, and now this calculation that we have done in step 3, that has become garbage. So we again have to delete something to add the thing into the system. Don't think so. the whatever I have written over here, first of all, it is not a garbage. This part is mandatory. These parts are also mandatory, because if I could have introduced artificial variables into the system from the beginning, then you could have asked me, sir, why is it so? Why is it happening? Because we understand the balancing system. Okay, balancing system is we understand, but why are you saying that always we need to associate one surplus variable with an artificial variable? Why is it so? So therefore, I have told you, first of all, I've told you the reason of doing so. Why, what fallacy appears in this type of case if we do not consider the artificial variable? This is the fallacy. This is the fallacy. And therefore, to remove the fallacy, we actually introduce the artificial variable into the system. Now your number of the number of variables has become 4 or 6, and number of equation remains 2. Now go to another page. I'm not going to the next page. You go to another page, and I'm going to do some sort of minor changes over here. Okay, I have the provision, so I'm going to delete something, some numbers, and I'm going to restate what I'm getting from the system. You do it afresh on the next page. You don't, erase anything that you have written. Everything is for understanding. So my step number 4, this is my step number 4 that I'm going to write. In number of variables, equations and number of variables will change. This will change, and this part will also change. This part will also change. So I'm going to make the changes over here. So number of equation now is 2. Number of variable is 6. Number of non-basic variables whose values will be determined is 6 minus 2 is equal to 4. 4 variables need to be put 0. What are the convention? Now I'm going to write the convention over here. You have got all the variables, all the type of variables which are required in LPP. So the convention of putting 0, let me write it in some other page, and let me write it in 3rd page. Okay, this is not a part of the problem actually. The convention of taking non-basic variable and giving it 0 value. So the convention is as follows. First, you choose original. Start with original. Okay. If all the original variables are exhausted, means you have considered all the original variables and you have put them with 0 value, but still you need to consider more non-basic variables. Then you go to slack. If all the slack variables are exhausted and you need to consider more non-basic variables, go to surplus. Now, if you have exhausted all the surplus variables, but still you need to put 0, you need to consider non-basic variables, go to artificial. This is the rule actually. This is the convention, but this will happen. Such a kind of thing will happen if the number of variables and number of equations are many, many more. Otherwise, it is not going to happen. But remember the convention. First of all, original. If exhausted, go to slack, surplus, artificial. Original, slack, surplus, artificial. Original, slack, surplus, artificial. Original, slack, surplus, artificial. Remember this rhyme. This is a new rhyme for MBA students. Now let's get back to the problem. So my non-basic variables are original, slack, surplus, artificial. Original. All originals have been considered. 2 more need to be considered. Slack variables are absent. So go to surplus. Put S1 equal to 0. Put S2 equal to 0. And now you see that your basic variable basic variables become A1 and A2 with positive value, non-negative value. A1 is 0, A2 equals to 2. A1 is 0 and A2 equals to 2. So we do not have any problem right now. We do not have any problem because it is satisfying the non-negativity constraints of the linear programming problem. Now you quickly put your attendance in the, write your student IDs in the chat box. I'm going to save the attendance. And meanwhile, if you have any doubt, you can ask me by unmuting yourself. The next part of the problem, that is the consideration of objective function, that will be discussed in the second session. We have 5 minutes 39 seconds left. So you put your student IDs. And if you have not understood anything, any part, you ask me. So I'm pausing the recording over here. Quickly talk about, let me quickly say about that. I'll again repeat that same thing. Yes.
স্যার বলছি অ্যাটেন্ডেন্সটা কি চ্যাট বক্সে লিখবো?
হ্যাঁ, chat box. Now you see the artificial variable. You could have asked me one question. We missed one point. You could have asked me this question, sir. Each select variable and artificial variables has some sort of per unit contribution, which is 0 in the objective function. What will be the per unit contribution of the artificial variable in the objective function? So it is a convention, another convention in Q. Another convention is in Q is that in objective function, the artificial variable is added with per unit contribution, which is minus m, and we write minus m a1, and for a2 also we write minus m a2. This minus m is actually remains minus m remains same for both a1 and a2. What is this minus m? What is this m? M is a hypothetical figure. Is a hypothetical figure which is which doesn't have any physical significance, and it is too large. And as if we are saying that the contribution of the artificial variables are not balancing variables. They do not balance the system. They help us to do the algebra. They help us to remove the fallacy. We, by convention, we cannot put 0 as per unit contribution to the for the artificial variable. So we choose another constant, which is denoted by m, and which is a very large figure, and we add it in the manner that I have done in this particular objective function. We write minus m a1 minus m a2, not plus m a1 and plus m a2, because of some reason. There are some reasons for doing that. We will explain in the next class. Next session. Sorry.